Okay, so we were talking about compactness. Now we're going to focus in on a particularly interesting metric space. And let's focus on trying to figure out what do compact sets look like in the space of continuous real-valued functions on the closed interval a to b. I need a metric, obviously, for my metric space. So remember that this we're thinking of as the set of, again, continuous real-valued functions defined on this interval. And we already saw that this is complete under this particular metric. So just the maximum distance between f and g, that is the maximum over all x in the interval of f of x minus g of x. Okay, do we remember what complete means, I guess? That's probably a first important question. Cauchy sequences converge, exactly. So we already know some important things about this space. Cauchy sequences converge. Now we want to know how to characterize sets in such a way that, well, what was our, Heine-Borel was our definition of compactness, but sort of equivalent to that was every sequence has a convergent subsequence. So we want to know, what do we have to say is true about a set in order that any sequence, from any sequence in that set, we can somehow extract a Cauchy subsequence. Okay. We can certainly come up with sets where that's not true. So, a generic subset of the continuous functions is not going to be compact. So here's an easy one. Let's consider the set of all constant functions. Okay, they're obviously continuous. They're as continuous as you could want them to be. But this is not going to be a compact set because we can certainly imagine writing down a sequence in here. Let's, for example, take this sequence, fn of x, is just equal to n. And everything in this sequence indeed lives in my set. And what's happening? These are just, okay, the first function is the constant 1, the next one is the constant 2, the constant 3, constant 4. There's not going to be any way to extract a convergent subsequence out of this because this sequence just keeps growing and growing and growing. And there's no way to make it converge to anything. There's no way to take out a subsequence and convert it to anything. So this has no convergent subsequences. So it can't possibly have come from a compact set. Okay, so I'm going to use a couple of these counterexamples, a couple of sets that are clearly not compact, to help us come up with some criteria that might give us compactness. So what's the real problem here? The problem here is that we've got functions that, again, we're just allowed to get bigger and bigger. Any particular function from here is certainly bounded. It's constant, it has a constant bound. But there's not a bound that works for all of these functions. They're just allowed to keep getting bigger and bigger. And that's a problem. Anytime we have functions that are allowed to just get bigger without bound, we're not going to have compactness. These things are not going to converge. So here, if we think about trying to prevent the issue that went on here, we know every element of T is bounded. Okay, so for you give me a particular function f, I can find a bound. Given that bound, I can certainly find another function in T that's not going to obey that bound. So you give me a bigger bound, but I find you another function that still doesn't satisfy the bound. That's a problem. So we're going to say, at a minimum for compact sets, we need a bound that works for everything. We need to keep these functions under control so they can't start exploding on us. So every f is bounded, but in this case, there was no bound that works for everything. Okay, so this is one condition that I'm going to put, and it's a condition that is generally going to be fairly easy to check. Do things stay bounded in a uniform way, or do they not? And this is good. We want to write down criteria that are easy to check. So we're going to call this uniform boundedness. So we say that set T, that's a subset of these continuous functions, is uniformly bounded if, now we already know for all f there exists some m that's a bound. I want to switch the order of those things, and I want to say there exists an m that works for every function, such that for all functions in my set and for all points in my domain, f is bounded by m. Okay, so this is one condition on our wish list as we're trying to build up compact sets. Are we happy with this condition? Any questions? So here's an example of a uniformly bounded set. Let's look at the set of all functions of the form x to the n. Okay, where n, say n is allowed to be natural numbers. Okay, and we're going to let our domain be 0 to 1. So this is a subset of the continuous functions defined on 0 to 1. Is this set uniformly bounded? Yeah, sure it is. Nothing in here can ever go bigger than 1 in magnitude, right? We have a power here that's bigger than or equal to 1. X is at most 1 in magnitude. So x to the n is never going to be bigger than 1. So for all f and for all x, f has the form x to the n, which is certainly going to be less than or equal to 1. And again, this bound 1 works for everything. So we're going to say this is uniformly bounded. Next question then, it's uniformly bounded. Checked off one of the criteria that we think we probably need. Is this set compact? What's that?
Under this metric.
Under this metric, yeah. Yeah, everything today is going to be under this metric. Because we know the criteria we come up with for compactness are going to depend on the metric we choose. So is this compact? Well, again, I'm going to use the criterion that if I have a sequence, I mean, I can easily, there's a natural, obvious sequence to pick out of here, x to the n. And we want any sequence to have a subsequence that converges to a limit in this space, or in this space, in this space. So let's think of a sequence. Let's consider this sequence. Okay, we can think of this converging pointwise. What does this converge to pointwise? Yeah.
0 or 1.
0 or 1, exactly. So a lot of the time it's 0, right? We take something less than 1, we raise it to a power that goes to infinity, and that goes to 0. The only exception is, if x is 1 here, I raise 1 to any power, and it just continues to be 1. Okay, so we have a sequence. The sequence has a pointwise limit, and we can write down what it is. And so I ask again, would you say that this is probably compact? You're shaking your head. Why?
Because it's not continuous.
It's not continuous, exactly. If this converges, then it's supposed to land on a limit that lands in the original space. That's the big deal about compactness. We have limits, and they stay in our space. This didn't stay in our set. So this is not in T. Right? In fact, it's not even continuous. Okay? So again, even though this is uniformly bounded, that wasn't enough to give us compactness. That's not enough to give us convergence to limits in our set. So again, this T is not compact. Okay, so let's, again, I'm trying to use these counterexamples, these non-compact sets, to try to give us some idea what went wrong that prevented this from being compact, so that we can try to exclude that from happening later. So let's think about what went wrong here. Well, f1, okay, is linear. And then later I have a quadratic function, cubic function. I mean, these functions all kind of look the same, but they start to be closer to 0 here and then steeper here. So this might be n equals 1, n equals 2, and so on. What's the problem that you see in this list of functions that's keeping us from landing on a continuous limit? Yeah, we're somehow losing differentiability. So, I mean, of course, every one of these functions is perfectly differentiable. But somehow this function is less differentiable maybe than this function, right? You're seeing that the derivatives are getting steeper here. So for each fixed function, we've got a finite derivative everywhere. But the derivatives are certainly getting larger here. They're getting larger and larger and larger. And in the limit, we're getting this breakdown of differentiability. And in fact, breakdown of continuity. Breakdown of differentiability is fine. We're not asking limits to be differentiable, but it's leading to somehow this breakdown of continuity. So we know every function in this set. Where did the set go? Here it is. Every function in my set is continuous. In fact, it's uniformly continuous because it's a continuous function on a closed bounded interval. So right now we know for all epsilon greater than 0 and for all f in my set, right, there exists some delta greater than 0 such that if x minus y is less than delta, then f of x minus f of y is less than epsilon. Okay, this is just a statement that we're starting with continuous functions on a closed bounded interval. So for any one of these functions at any epsilon, I can certainly pick a delta. But what we're going to find as we go down the list here, this delta is going to change, right? So for n equals 1, if my tolerance, say my tolerance is epsilon here, well, here's 1. And for n equals 1, I land about here. This is going to be my delta corresponding to n equals 1, right? I'm going to have a pretty big delta. Now we start going down the list. what if I want to get to n equals 4? Well, n equals 4, I'm all the way out here. All of a sudden for n equals 4, my delta got a lot tinier. And what we're going to see as we go down the list, keep letting n get bigger and bigger, right? These things get steeper and steeper and steeper. This delta is going to get tinier and tinier and go to 0. So there's not one delta that works for everything. You know, just like in the last case we said, everything has a bound m, but there's not one bound that works for everything. Here we have this issue with continuity. It's always there, but it's somehow breaking down or blowing up in the sense that this delta doesn't work for everything. It has to keep getting smaller and smaller and smaller as we progress down our sequence. So I'm going to do the same kind of thing that I did for this issue of boundedness and say, no, I want something stronger than this. Before we said I want an m, a bound that works for everything. Now I'm going to say, actually, I want a delta that works for everything. If I have a delta that works for everything, then it's going to keep these things from getting steeper and steeper and steeper. And this we're going to call equicontinuity. Equicontinuity, these functions are equicontinuous in the sense that somehow there's a delta that works for everything. And that's really going to be equivalent to we're keeping the Lipschitz constant under control. I'm not asking for differentiability, but we're keeping Lipschitz constant under control. Things can't change too quickly. Because changing too quickly is what killed us here. So we're going to say that a set is equicontinuous if, okay, again, it's going to look like the usual definition of continuity. I'm just changing the order of things a little bit. So if for all epsilon greater than 0, now instead of choosing my f and then working out what delta is, I'm going to start by saying, actually, I can find a delta that always works. So for all epsilon greater than 0, there exists some delta. Okay, so if this is the delta I picked that worked, that's going to prevent anything from being so steep that it suddenly wants a much smaller delta. Because wanting this tiny delta is equivalent to things changing really quickly. For every epsilon greater than 0, there exists a delta greater than 0 such that, okay, now I can say this delta works for everything. For all f belonging to the set, and for all x and y, such that x minus y are less than delta, the function will change by an amount less than epsilon. Questions on the concept of equicontinuity? You know, it really is just a statement we're limiting how fast the functions are allowed to change. Just like with uniform boundedness, we said we're limiting how high the functions can go. Now we're limiting how fast functions can change because we think that's something that can break continuity in the limit, and we don't want to break continuity in the limit. Okay, so let's take another example of a set. Let's take functions of the form sine of nx divided by n. And let's try to decide if this is uniformly bounded and if this is equicontinuous. First, uniform boundedness. Is this uniformly bounded? Gabriel's nodding. Sure it is, right? The sine function is always bounded by 1, and then we're dividing by something that's at least equal to 1. So this function is never going to get bigger than 1. Okay, so for all functions in our set, right? And let's say for all x belonging to 0, 1, or whatever our domain happens to be, f of x, right, is equal to sine of nx divided by n for some n. All right, this guy is bigger than or equal to 1. This guy is less than or equal to 1, so the whole thing is less than or equal to 1. Right? So we come up with a bound of 1. This doesn't depend on n at all, right? This works for everything. So this is certainly uniformly bounded. All right, and then the second question is equicontinuity. All right, to check equicontinuity, all right, we have this technical statement here. If the functions happen to be differentiable, it's really just let's check the derivative and see if the derivative stays bounded, right? I said, and I'll do it explicitly, but I said that this condition is really just limiting how fast things can change. It's limiting how big the derivative can be. My derivative is not allowed to blow up. If we don't have differentiability, well, it's limiting my Lipschitz constant. My Lipschitz constant can't blow up. So in this case, if we take a function out of our set, we take its derivative, all right, the n comes out and disappears the one on the bottom, and we get cosine of nx, which is certainly bounded. Okay, so I mean, you can either argue this is a mean value theorem argument. You can just state this bounds the Lipschitz constant. We know that the Lipschitz constant is always bounded by the largest value of the derivative. So this means that the Lipschitz constant of f is also less than or equal to 1. All right, that's actually enough to check equicontinuity, and I'd generally be happy with you stopping here, but I'll argue it through once just so that you see why this gives us this. Okay, so let's let epsilon be bigger than 0. And f is in our set, and x and y are in our domain. All right, we know if we're trying to recover our equicontinuity, our conclusion has to be something about f of x minus f of y, right? So it's kind of a usual continuity argument from the definition, is that we just manipulate it until we can force it to be less than epsilon. So right away we know, well, this is less than or equal to the Lipschitz constant of f times the size of x minus y. Well, whichever f you chose doesn't matter. The Lipschitz constant is at most 1. You know, if you like it better, you can treat this as a mean value theorem, and this is equal to the derivative somewhere times x minus y. It's the same kind of argument. So this is less than or equal to x minus y, and I can certainly make this less than epsilon, as long as x minus y is less than epsilon, which becomes my delta. Right? Now this delta doesn't care which f I chose. Right? This delta works for all the functions in my set. And that's the key that gives us equicontinuity. So this delta works for all f. So we can say, indeed, we have equicontinuity. Is this set compact? It's uniformly bounded, it's equicontinuous. We think those are two important conditions.
0, the limit goes to 0, right?
For x equals 0, the limit would be 0, yes.
Right, x non-equal to 0, the limit goes to 1.
Well, what happens as n goes to infinity?
The limit goes
What happens to this as n goes to infinity? I mean, the numerator does something, but it stays bounded. The denominator blows up. So this is actually going to always go to 0. Okay, so if, for example, we consider the sequence, the obvious sequence to consider here, this converges to the 0 function. Which is a beautiful continuous function. That's good. We'd like limits to be continuous. Is this set compact?
We're going to say if we find it in subsequence.
Yeah, so I mean, we have to be able to say that every sequence has a convergent subsequence that converges to a limit in the set for compactness. Does this function live in our set? No, it doesn't, right? There's no value of n that makes this the 0 function. So we're so close here. We've got, at this point, a sequence that does converge to something that's continuous, which is good. The problem is it's not in the set. The set doesn't contain its limit points. So actually the last thing that we need here for compactness is the set should be closed. It needs to be uniformly bounded and continuous. That's enough to give us subsequences that converge to something continuous. Then if we take the closure of the set, it will contain its limit points and we're done. Okay. I haven't proved that. I've given some intuition on why we're getting here. So this 0 function is still not in T, but 0 is a continuous function, certainly. So while the set T is not compact, actually the closure of T is compact. I just have to add the 0 function, actually. So T bar, actually, it will turn out, which is going to be this together with its limit point, is compact. Again, I didn't prove that to you. I'm just trying to give intuition here. So those are actually the 3 conditions we need: uniform boundedness, equicontinuity, and closedness. Okay, that gives us compactness. And so it's not the same as being closed and bounded like in Rn. It's a different set of conditions, but it's a set of conditions that's straightforward to check. Now, in practice, we don't so much worry about is the set closed, because most of the time, not always, a lot of the time, what we really care about is, does this converge to a continuous limit? Okay, this guy didn't converge to a continuous limit. No, it wasn't in that set, but yes, it is continuous. So I'm going to state this theorem the way it's usually stated in analysis. This is called the Arzela-Ascoli theorem. Okay, so let's suppose we have a collection of functions, which I'll denote by script f. And this has the nice properties we've talked about. It's a collection of functions that are uniformly bounded and equicontinuous. Okay, and these all lived in our set CAB, in our space CAB. Now, the result is, okay, not that script f is compact necessarily. Script f bar is compact. The closure of this is compact. What does that mean? That means that given any sequence of functions, call them GN, that belonged to script F. We can extract a subsequence that's going to converge to a continuous function. So there exists a subsequence that converges uniformly to a limit in, maybe not in this family, but in the closure of this family, which is still a continuous function. Okay, so what does this mean? I mean, this is a really powerful result in analysis, and it extends pretty easily to other metric spaces beyond the continuous functions as well. You just got to tweak a little bit what you mean by these concepts. And this would be a common result for proving existence of solutions to differential equations, for example, existence of minimizers if you have a variational problem, which are used to model a lot of different things in biology, applied math, engineering. But it really just says, all right, maybe you have your sequence that you've devised somehow. You want to know if it converges or if it has a convergent subsequence at least. Well, there's really just two things to check. And they're not super hard things to check, you hope. Right? That you just have to check there's a uniform bound for everything in your sequence, and that they're equicontinuous. Now, of course, in real life, I'm not going to have a family of functions maybe that's given by some simple explicit expression like this. They're given by some iterative process. But nevertheless, these are conditions that are relatively straightforward to check for a lot of even very difficult underlying problems. Okay, so how do we get there? And let me outline the proof at least. We're going to start by saying, let's try to come up with functions that converge at all the rational numbers. Because there's not so many rational numbers in some sense, right? The rational numbers are countable. We can put them in a one-to-one correspondence with the counting numbers. So what I'm going to do, I put the rational numbers in a list. And now I'm going to come up with a subsequence that converges pointwise at just the first rational number. That's all I care about. All right, so I have something that converges at the first rational number. Right, now I say, well, let's extract a further subsequence and make it converge at the second rational number. Okay? And it still converges at the first rational number. And now I keep going. Let's extract a further subsequence that converges at the third rational number, and it still. And at the end, you get this subsequence that converges at all the rational points. And you say, well, the rational points are arbitrarily close to the irrational points, and you kind of get the result for free. So that's the outline of the proof. So I say, let's let xi be some sequence that hits every rational number in our domain. And then we say, let's look at the set. Okay, I have a sequence. I'm only going to ask what the sequence does at x1, the first rational number, whatever it is. Okay, so this is now just a sequence of real numbers. It's not a sequence of functions, it's just a sequence of real numbers I'm looking at. It's certainly bounded, right? Because we started with a uniformly bounded collection of functions. So this is certainly bounded. What do we know about bounded sequences of real numbers?
Convergence.
They have a convergent subsequence, right? So, I'm trying to like bootstrap my way up from what I know about the real numbers to doing this at continuum of points. But we know there exists a convergent subsequence. Okay, so I'm going to denote this subsequence. I don't want to let the notation get out of control here. So this is my first subsequence that I've taken. Right, that's what the superscript means. This is my first subsequence. Okay, and we know that. Okay, this is a collection of functions, and I know that this limit exists. We've only asked what happens at the first rational number. Nowhere else. So, but I know at least at the first rational number, we get convergence. Now I take this family of functions and I play the same game with this sequence that I did with this sequence. Look at the set. All right, I have this family of functions, a sequence of functions. Now let me plug in my second rational number. Well, again, this is just some bounded sequence of real numbers, so it has to have a convergent subsequence. All right, it's still bounded. So once again, there exists a convergent subsequence. Which I'll denote by f and 2. Okay, so this is a subsequence of this, which is a subsequence of this. All right, and now we know this converges at the point x2, and it still converges at the point x1, because everything in here originally converged at the point x1. So now we know that these limits exist. And now we just keep going. We keep doing the same thing over and over again. We keep extracting subsequences to converge at the next rational number, the next rational number. Right, and in general, so I'm at the case level. So this was a subsequence of the k minus 1 subsequence. That was a subsequence of the second one, was a subsequence of the first one. It's still a subsequence of my original. And now it's going to converge at the first k points. All right, so now I have a list of subsequences. From that, I need to say, what is this guy going to be? The final subsequence that converges. Okay, so let's define one more, our final ultimate subsequence. Okay, I'm just going to call it Fn with no superscripts. Okay, this is the final one that we want to talk about, and it's going to be our GNK. Okay, I want to not have that notation to write it all the way through. Okay, so what am I going to do? The first term in that sequence is going to be the first term in my first sequence. Okay, so this was a sequence. I'm going to take the first function in this sequence. The next one will be the second function in this sequence. then the third function in my third sequence, so on, the k function in my k sequence. It's like a diagonal argument. Like if you remember Cantor's diagonal argument, it has that flavor. Pick the first element of this guy, second element of the second guy, the third element of the third guy. Okay, so we're going to define F1 to be the first element of the first sequence, F2 to be the second element of the second sequence, and so on. Okay, now all of these guys are still, have still been extracted from my original sequence. Where did it go? Here it is. All of these guys have been extracted from here. They're particular elements in here. We skipped some along the way. So this is certainly a subsequence of the original. But now this is a subsequence that converges at all the rational points. Right, we've designed it to converge to all the rational points. I couldn't do this argument using all the points in my whole domain because there's a continuum of them. I can't create a sequence of them, but I could create a list of these rational numbers. So I've made this converge to for all the rational numbers. Now the goal is to say, well, if it converges to all the rational numbers, it can't do anything wildly different nearby, and nearby, in some sense, should cover all of the irrational numbers too. So this is our goal. Let's show that Fn of x converges everywhere. So what I'm actually going to say is, let's show, we have tests for convergence. Let's show it's Cauchy. CAB is a complete space, so Cauchy gives us convergence straight away. So let's show that this is a Cauchy sequence. So let's write down the things that we know. We know a few things. We know it converges at the rational numbers. So I'm going to write that down. So let epsilon be bigger than 0, then there exists some n star. Okay. Right now all I know is pointwise conversion at the rational, so it could be a different n star at each point. Okay, such that if m and n are bigger than n star, then fm of xi minus fn of xi is less than epsilon. Okay, again, this is just a statement that we know our function converges at this particular rational point xi, so it must be Cauchy at that point. Let's call this fact 1. Fact 2, I mean, we've got to feed in information about the irrational number somewhere. Fact 2 that we haven't used yet is, I mean, I've used this property a lot. Everything is bounded uniformly. I haven't used equicontinuity yet, and that probably is important. We know it's necessary. So let me write down equicontinuity. Right? Equicontinuity says there exists some delta that works for all these functions. There exists delta greater than 0, such that if x minus y is less than delta, then fn of x minus fn of y is less than epsilon. And this doesn't apply just to rational numbers, this applies everywhere. And it applies for everything in my sequence because equicontinuity. They all have, the same delta works for everybody. Now let's string these results together to come up with a statement that actually my overall sequence is Cauchy just globally given the usual metric on continuous functions. So what's the big thing I need? Well, you have an epsilon. We picked our epsilon. I need an n star. Well, right now I have infinitely many n star, which is too many. I just need one n star that will work. So, I mean, usually if they have a whole list of n star, I say let's just take the maximum of them and we're good. I'm not quite in a good position to do that yet because there's infinitely many of them. So we've got to reduce the number of n stars that we have to work with. That's our first goal. We can do that. Good news. So let's notice this. Our domain is closed and bounded. It's compact. Now what I'm going to do, I'm going to break it up into a few different intervals. So here's A to B. And I'm going to just break it up into a bunch of different intervals of width delta, where I can use, where anywhere in here I can do a comparison and use equicontinuity. Okay, I'll do it again, some other interval, some other point. Again, I really only need finitely many of these intervals to cover my domain. That's compactness. So I'm going to define these sets, ui, as just these intervals, the rational number minus delta to the rational number plus delta. Okay, you want to use technical language. All of these UIs together form an open covering of my domain. Domain is compact. We know we don't need infinitely many of them to cover it. We need finitely many of them to cover it. Okay, so we can find, okay, here's Jaime Burrell trying to sneak in again. Well, it's not surprising maybe, all these things we know about compactness and convergence are the real numbers. We're just trying to kind of bootstrap to make this work for functions. We can find finitely many of these sets. Let's say, I'm going to pretend that I labeled my rationals in a really clever way at the beginning to make this work, that it's just the first K. Without loss of generality, I can say that. This is how I label things. I mean, I could explicitly do that. I could explicitly come up with a list of rationals that covers this. Okay, that cover the domain. So what's going to turn out to be the case is that although I technically have infinitely many n stars, the only n stars I'm going to care about are the n star corresponding to this point, just the n stars corresponding to the center of these intervals. So let's let n star be bigger than all of those. Right, that gives me a candidate n star. That will be enough. Now, in a couple lines, we can string these statements together in a way that says, actually, my overall thing is Cauchy. So what do I need to do to show this is Cauchy? Well, let's just pick any point in the domain. And let's pick any m and n bigger than n star. I'm going to have to use this to somehow. So x might not be rational, so I've got to compare it to a rational. So I'm going to use this statement to compare it to a rational. X will be a rational, I'll pick in, x is whatever it is. Y will be some rational number. And then I can use this statement. So how am I going to pick that? I'm going to say, well, over here somewhere is the point xj, and my point x lives in one of these intervals, right? These intervals cover the domain, so x is in one of them. And whatever the center of the interval is what I'm going to compare it to. So x belongs to uj for some j. And x minus xj is certainly less than delta. Okay, x minus xj is less than delta, so that means I'm allowed to use statement 2 here. Okay, it's also true that n star is at least as big as nj star, so I'm allowed to use this. Okay, so I'm finally to a place where I can take these simple statements and actually use them. So let's try to string this statement together. What do we want to do? I want to show that this is a Cauchy sequence, so I need to compare two different terms in my sequence. Right, so we do our usual thing, and let's try to break this down into things that I know how to talk about. So fnx, what do I want to compare f of nx to? Well, I guess this doesn't work because x might not be rational. I need to use this thing. So I would like to compare it to something rational, and we said xj is the thing I want to compare it to. So let's put a fn xj there, and then I need to add it back in. Well, now I'm at a rational point, and I have an n star that is perfectly valid. My m and n are certainly bigger than this. So now I can use this statement to jump from n to m. Okay, I need to add it back. All right, so I've jumped from n to m. Now I have an xj here. I need to get back to x. Well, I'm in good shape to do that via this statement here, okay? Remember this, I've written n here, but this works for every n, equicontinuity. It works for every gut buddy. So I don't need to change deltas in order for this to work for m. So now let's go from xj back to x, but just at this different point in our sequence. Okay, and we've set this up so that each of those terms corresponds to either this or this. They're all less than epsilon. Okay, right, so it doesn't matter which functions I picked here as long as I passed n star. It doesn't matter which value of x I picked here. So in particular, that means that the maximum of them will also be less than 3 epsilon. And that's the statement that we have a Cauchy sequence in the space of continuous functions, right? This is the metric we've been playing with all along now. So we've said now, given an epsilon bigger than 0, I can somehow construct an n star. This should probably be an I star. I can somehow construct an n star such that as long as m and n are bigger than n star, the metric between fn and fm can be made as small as we like. So indeed, that's what we wanted to show. So what did we find? We found a subsequence. Subsequence fn, which I could write this way. You know, there's some way it's a subsequence of our original. that is Cauchy. CAB, we've already seen a week or two ago that that's a complete space, which means Cauchy sequences converge and the limits stay in the same space. So we can say right away, this subsequence converges uniformly to a continuous limit. And that's what we wanted. So I'll pause. Questions? It's a biggish proof. I don't know if it's the worst one we've done this semester, but it's a biggish proof. But again, it's the nice setting where we do this big proof once, but now we really have two pretty simple conditions to check if I want to start asking questions about convergence of continuous functions to continuous limits. Right? Which is a big question, a hard question. You wouldn't want to go through this nonsense from scratch every single time. But to do it once and then be able to use it, that's fairly powerful. It's a nice little argument. It's a bit of a clever argument. It's not midterm or final exam material to like reproduce this from scratch. But of course, stringing things together like this is things that you're expected to know how to do. Dreaming up a weird diagonal argument like this, maybe not on the fly. But it's good to see where these things come from and believe they're right. And then let's do an example and actually use this. Okay, so realistic example. This is maybe the most this is not a toy example. This is a real example now. So existence of solutions to nonlinear ODEs. So let's consider the initial value problem. X prime of t equals f of t and x with some initial condition. Okay, fairly standard looking first order ODE. We want to know, we'll write down some extra conditions. We want to know, do solutions exist? That's a non-trivial question. You could easily write down ODEs where solutions don't exist, or they fail to exist after some finite time. So this is a thoroughly non-trivial question. All right, and F can be nonlinear, so it's not going to be straightforward necessarily to just construct these things. I'll give you some conditions though. Let F be continuous on the domain minus RR to minus cross minus RR. Okay, so as long as we plug in x's and t's that are less than r in magnitude, f is supposed to behave itself. Then the claim is there exists a solution, x of t, that is defined on the same time domain. Okay, so I'll give you the setup, but then what we're really going to do is we need a sequence. If we're going to use isosceles, we need a sequence somewhere. So the goal will be to construct a sequence that we hope is trying to approach the solution of this. Right now, we don't know that this has a solution. We're going to try to construct some sequence. Then we're going to use arzelastally to say, well, yes, we can check this as uniformly bounded. Yes, we can check this as equicontinuous. That means the sequence does converge to something, or at least it has a subsequence that converges to something. And then you go ahead and say, well, let's take the derivative of the thing that it converges to and check that indeed the limit satisfies this. So, how are we going about this? Let's use a fundamental theorem of calculus to rewrite this a little bit. That this intermediate value problem is equivalent to this statement. Okay, I need a sequence. What I'm going to do is generate a sequence. Things like this, I can kind of start to build. I'm going to build them out of, now I can't just take my right-hand side and then say, let's do this integral, because I don't know what x to put in here, right? So it's not as simple as saying, oh, this is integrable, you're done, because I don't know what x we're going to put in. What we're going to do is treat f as piecewise constant and have piecewise constant things that we really can't integrate. And then we're going to let the little subintervals this is constant on shrink and hope that we get a nice continuous limit. Okay, so let's approximate this by treating f as a piecewise constant. All right, so what do I mean by this? I'm going to partition my time domain. Okay, time in this way. Okay, so a usual partition, a usual uniform partition. Okay, the usual thing that the space between all of these is equal. Okay, and then what I'm going to do is say, well, from 0 to t1, okay, I'll just approximate f by its value at 0. And now I have a constant and I can integrate it. That gets me to t1. Then I take whatever I had, integrate it again to get to t2. And again, I'm just integrating constants every time. Constants, okay, I know I can integrate. So let's approximate f by its value at the most recent time step. Okay, so I'm going to generate a function that I'm hoping approximates the solution to this. So at 0, it's just the initial condition. Now, for later times, I'm going to say I don't know what f is everywhere, so let's just put in what it was at 0 and do that integral. So I'll say xn of t is x naught plus, and now again, I just do this integral treating f as a constant. Okay, and I'll keep using this approximation until I get to my next time step. Well, if I want to get bigger values of t, I need to integrate farther than that. So I'll say, well, I integrate to t1, and then I'm going to do it, say, what was that? Now, pause again, what was that? Integrate my new f to t2, or however far. So my next, from here I go, let's take what I had. And now we do a new integral. X and of t1 ds. Right, so it's just freeze. What was at time t1? Let's figure out what my approximation to x was. All right, and plug it in here. Freeze t1 here. So this is still a constant. This should go from t1 to t, sorry. The time domain, right? T1 and t2. And we keep doing this. We just keep integrating until we get to the end. And in general, xn of t, okay, involves these little integrals of constants. So it's just f at the old time times whatever the time interval was, f at the next time times whatever the time interval was, and we keep going. So x naught plus, now we sum over all of these. So f at whatever the beginning of the time interval was. Times the length of the time interval, and then maybe a little bit left at the end. J. Okay, so there's a little bookkeeping to write this all down right, but it's not a complicated idea. We're just doing something numerical, I guess. Just saying, let's treat this as piecewise constant. So it's an Euler iteration. Now the goal is to do two things. We have this sequence of functions now. Different values of n correspond to how to find my partition is. We want to show this is uniformly bounded. We want to show it's equicontinuous. If we can do those two things, then boom, we have a continuous limit, and we can then go ahead and check and see if this is true about our continuous limit. Is this uniformly bounded? I mean, I've suggested the answer is yes. I've suggested this will work, but the real question is, why is this uniformly bounded? Because what? So this part matters. F is continuous. Right, if F could just be anything, we'd be in trouble. But what do we know about continuous functions that are defined on a compact set, a closed bounded set? What's that? They're bounded, yeah. F is bounded. We're just adding little time intervals on here. So F is certainly bounded. Okay, so xn anywhere is going to be at most, well, x naught plus m times my local time step plus, well, I guess one more m this is just a telescoping sum, right? So this sums up to Tj minus T naught, which is 0. So this adds up to Tj plus T minus Tj. This is bounded by x naught plus mt. And since we're working on a finite time domain, we've got a bound. And this works no matter how refined my partition is. And then using exactly the same bounds on F, I'm not going to do the details because I'm short on time, but using the same bounds on F, right, you can show that again, everything just simplifies to F being bounded by M. And this can always be made less than epsilon. Okay, again, it's just a couple lines of careful bookkeeping, but there's nothing fancy you need to do to get this. Yeah?
The x prime equals f of t and f is bounded.
You use the x prime, yeah, x prime equals f of t, and f is bounded. So that's the last step to show that your limit works. But this is enough to say xn has a convergent subsequence. With a limit x of t that's continuous. Right, and from there, again, it's just a little bit of bookkeeping to check that it satisfies your ODE. Right, so a challenging result, to be sure, but one that's not very hard to prove once you have the power of R's law Ascoli. And here, this comes up in all kinds of different existence theorems in differential equations, calculus of variations, and so on. Okay, so I'll leave you here, and then we'll finish up with concept of continuity on metric spaces next week.